Good afternoon, good morning, buenos días, buenas tardes. As Giuseppe was saying, we're going to talk today about mixed reality tools for visualization of complex spatial data in geomatics. I have a little bit of text at the beginning. There will be some videos at the end, and of course, questions. If I'm not sharing the screen or there's any technical issue, just let me know, and I will solve that. This is what we're going to see today. We're going to see a little bit about us, BGC Engineering, what's the motivation behind this presentation, what's the technology that we use, the data types. Then I will present some case studies, and finally we'll finalize with some extra thoughts and things that we can do after that. About us, BGC Engineering is an engineering consulting company. It's international, and we provide specialized professional services in applied earth science. And we do that for all phases of the project. We do that from pre-feasibility and design to construction, operation, and closure. I included some photos below of some of the recent projects that we've been involved. At the bottom left, that's a water retaining dam in the Northwest Territories. That's the Arctic Circle for a diamond mine. In the center, you will see one of the most recent landslide stabilization projects that we've been working on. And on the bottom right, mining. We do quite a bit of tailings dam design and construction supervision, QA, QC. So it's a little bit of a snapshot of what we do. And our purpose is to pioneer responsible solutions to complex earth science challenges. And with all of that in service of society. So we'll talk a little bit about the motivation. When I was preparing this presentation, I look at some of the goals of the GeoRisk and pre-move. I highlighted some that align very well with what we are going to discuss today. We see that we need to communicate with authorities and population. We need to transfer knowledge to experts and non-experts. And we need to develop new tools and then pass those tools to the responsible parties that will be working and managing risk. But how do we do that? How we communicate with them? And for the purpose of the presentation, I want to highlight that the concept of non-experts will also include trained professionals that might not be familiar with a specific challenge being discussed. For example, myself, I might be a geotechnical engineer, a lot of experience in mining, but maybe we are on a mining location where I'm not used to work. I might not follow the discussion the same way that I will follow if I will be very, if I will be part of that project. I will add a quote at the bottom. That quote is from Melinda Marshall from one of her TED Talks. It's called Talk Nerdy to Me. I'll strongly recommend that talk to everybody. We desperately need great communication from our scientists and engineers in order to change the world. We're fascinated by what you are doing, so tell us about it, but do it in a way that we can understand. On a way, if you are not able to present your information, if society, either experts or non-experts, don't know about it and don't understand it, then the work is not done. Technical experts need to be better at communicating with non-experts, especially when we are communicating uncertainty and risk. Risk terminology is still very confusing, and non-technical people cannot understand what we're talking about. Still today, there are researchers and engineers that do not agree about what's risk and how to communicate it. So how we can describe risk and communicate it to the people that's interested and those decision makers. At BGC, we want to be leaders in communicating engineering designs, risk, and complex applied earth science. That's why we're doing what we're doing, and that's why I'm here today. We want to communicate not only with communities, clients, and stakeholders, but we also want to communicate effectively within our project teams, with our colleagues at different consulting companies, and academia. And we want to do that to help society, to understand what are the needs, and to make sure that the needs are met at the end of a project. And hopefully we'll be able to reduce the number of tragic events like the ones I'm showing the screen today. You can see a rock slide that derailed a train. There were some fatalities involved on the top left figure. And at the bottom right, that's a pipeline rupture as well because of geohazards that resulted in fatalities and lots of damage. This pipeline was supplying gas to New York City, and that was closed for quite a bit of time. So quite a bit of impact to society and communities. We need to allow your work to be understood. And based on our experience, this is our subjective experience based on the work that we do. You need to be able to present all your data together. You need to be able to integrate all that data and look at them at the same time. You need to provide the right level of sophistication. It needs to be as simple or as complex as needed, but not more so. It's important to mention that sophisticated, it's relative, and what was yesterday very sophisticated and difficult, it's not today. And the world is changing fast. So it's our duty to be informed of what's new and exciting, and keep evolving and improving and incorporating those things in our work. It needs to be a collaborative environment. The concept of multiple drivers integrating the data together, not one driver, as I'm doing today, by the way, one driver and multiple passengers just listening to what person it's doing. My favorite one, show, not tell. Engineers and geoscientists, we love to take data, we have a bias on data, and then we come with conclusions, and then we try to convince people about what we are telling them. Different brains interrogate data in a different way. People might see things that we are not seeing. So let's show them the information. Let's shift from I'm an expert, trust me, to let me show you, and then I will answer all the questions that you have. It needs to be immersive. We understand data better when it's presented in 3D. Compared to a traditional static 2D screen, that extended presence of being on an immersive 3D environment provides enhanced problem solving, high levels of engagement, improved understanding, and much more. We need to be able to interact with data from any angle at our own speed with clarity and accuracy at any point on time. And then finally, no size limits. Scale is important. Seeing a photo of a rock outcrop, it's not the same as standing in front of that outcrop and understand the mechanics and whatnot. We started our journey by creating a geotechnical asset management platform where we could integrate our project data and visualize it on a more natural way. We call it Cambio. We use it every day. Our clients use it as well. For example, as we see on the screen, we can integrate INSAR data on the left and LiDAR change detection, it's shown on the right. But it can be instrumentation, surface mapping, geological model, you name it. Any kind of data can be integrated nowadays. Data collected during monitoring can be shown in ways that are easier for people to understand. And we want to use techniques from other industries that deal with real world data. Let's take a trip. This is a short video that we can show how it's a more natural way to present the data when we are standing on the ground and we're allowing people to rotate and see that topography, different vintages of LiDAR. You can see how it's changing. Now there's a buttress, now there is no buttress. But not only that, I can just start flying like I will be a raven, and I can start looking around by just using my mouse as a control, and I can rotate, have a better understanding of that topography, see where the problems might be. I still don't have that sense of scale, and I'm still seeing this through a 2D screen. But as you can see, this is a far more intuitive way to understand a topography than just a contour map. A lot of people has a very easy time at seeing a contour map and seeing if that slope is steep or it's not as steep, et cetera, et cetera. Other people will see a contour map and will not understand it. And by other people, I mean, for example, here in Canada, we have First Nations groups. They have a hard time. On the bottom left, you can see that I'm activating another layer, that's LiDAR change detection. That information is being pulled from the cloud in real time. I can change the parameters. In this case, I'm changing the minimum detectable absolute distance and the maximum absolute distance. I can adjust that and it will change dynamically. So I can see effectively. I can also superimpose INSAR change detection data. Again, it's being pulled in real time from the cloud, so I can play with it and change it to a scale or to a refinement that makes sense to me. So again, I'm not a passenger. This is me controlling my own experience from the angle that I want to be able to make sense of that data, to be able to understand where the limits of that landslide are located, et cetera, et cetera. As you can see now, I'm bringing the vectors from that INSAR one more time, trying to help the user to have a better experience and understand that better, that data on a better way. As I said before, we're still showing this 3D multi-layer geotechnical data on a 2D screen. So the 3D data is trapped on a 2D screen and 2D drawings. As you know, we usually prepare cross sections and we show information to people as a drawing that has cross sections, and then we need to pass through 10 or 12 cross sections, and mentally we need to construct that geological model or any kind of 3D complex challenge that we're facing. So why we do that? So we continue looking for ways to improve how we communicate, and we found the HoloLens headset. As you saw before, Giuseppe was wearing it. It goes in on your head, and you can see through it. So in contrast with virtual reality, which it's completely opaque, so you cannot see, you feel isolated. In a way, you jump into the digital world. With mixed reality, you liberate, you take that 3D model that it's trapped on a 2D screen, and then you dump it in the middle of the room. You can still see your surroundings, so you can walk around, and I will show some videos. You can still walk around, and you can still talk to people. So it's a far more natural way to communicate. Not only we can show all the data together, but you can drive your own experience. You can walk around, as I was saying, and I will show some videos. As shown in this image, this technology has been successfully used to communicate complex projects to multidisciplinary groups, including technical and not technical experts. Top left, you can see at BGC an internal technical review meeting. On the top right, and I will talk about that photo a little bit more in future slides, it's a review meeting from an independent panel of experts. Bottom left, of course, you can do this solo. You can be alone and make sense of the data by yourself. This technology has successfully been applied in community engagement meetings. You can see from all age, from elders to young kids, everybody understands the data on a better way. And of course, decision makers, government officials, you can see even a policeman. But all of them can discuss those challenges by walking around the same model as a 3D hologram. How that looks like, I will start me rotating, not me, like two junior engineers rotating that 3D model on the screen. This is a rock outcrop. They have a photo, fantastic photo that helps them to point, but the one on the left is a passenger. The one on the right is controlling the experience. Instead of that, they can just deploy that same model in the middle of the room. This is one of our offices. Someone else from the distance can join the session from a hotel, from their home, from wherever they happen to be. And you can see on the image, there will be a white dotted line. That's the person that it's present. And then you can see a hologram of that HoloLens floating. That's the person that's in another space. And you can see that blue line, that's that person pointing. You can see here again, a third person can join the session. Up to 10 people, the technology right now allows us up to 10 people to join that session. And you can make things big. This is the one-to-one scale. This is the life size rock outcrop scan that was done. And you can see them discussing specific details that I will not discuss today, specific details about that rock outcrop. And they can do that like they are in the field. This is me. They send me that same information, and I'm on a construction site here in Vancouver, and I deployed this in the open air. So you can use it anywhere at any time. You just need to have that HoloLens on your head, and you will be able to see. And here I'm like kind of climbing the wall. I'm kind of bringing the model down so I can interrogate the top of that rock outcrop. So this is how this technology looks like. What kind of data we can show? So far, the limit is either your imagination or the computing power of the device. So this device is a self-contained computer that has the screen in the front. Technology is evolving. I know that Apple is producing their own headsets. Not sure when that's going to be released, et cetera, et cetera. So technology will evolve, and we need to catch up with that technology as it evolves. This slide shows some examples of common data types that we work and that we can combine to assess geohazards, including satellites from the top, far away from the planet Earth. We have satellites, airborne LiDAR, aerial photogrammetry, and one of my favorites, down on the ground, foots on the ground, we have 3D models created using iPads and iPhones in a matter of minutes, and I will show that in next slides. This is how it looks like. The videos I will show now, it's me looking through the HoloLens and recording it. So you can see what we call a tabletop model. So it's a 3D model, which is a hologram that it's floating on top of a table, and me walking around Again, you have the, I'm still showing this on a 2D screen. You need to see it. You need to grab one of the HoloLens and experience it by yourself to fully understand and appreciate that 3D component. On the right, me again on a park. You can see the beautiful flowers and the trees here in Vancouver. And I'm looking at another model. In this case, it's a structure from motion photogrammetry for one of our projects here in Canada. This is all field data surface for large areas. On the left was LiDAR and an orthophoto. Now I'm getting closer to the elements, and these are smaller models. On the left, one of these models that I was talking before about, with my iPhone on my iPad, I can now do a scan in real time in less than 2 minutes, and I can have this 3D model submitted and uploaded to the HoloLens, and anyone in the world, anywhere in the world, someone can grab that model and walk through it as I'm doing on the left, and here one of our offices as I'm in the field looking at that test pit. On the bottom left, I put the photo for contrast. It's far more dynamic and interesting to look at the 3D model than just the 2D photo. Now on the right, another of these 3D models. In this case, this is a rock foundation. And again, I put it on top of the room. I can walk around, I can get closer, I can change dimensions. I could see it at 1-to-1 scale and have the impression that I'm actually walking in the field, and I can have other people joining me, and all together we can discuss details. And you can see I'm looking at some concrete that was placed to smooth transitions in the rock, etc., etc. Those models are very detailed. Going now underground. On the left, you can see some boreholes. All those lines you see are vertical inclined boreholes. This is my house. I apologize for all the couch and everything, but you will see all those lines. Those are the boreholes. The gray discs, those are the results of permeability testing. So the smaller the disc, the less permeable the unit is. The bigger the disc, the more permeable it is. Now I brought a section of our geological model. So as I said before, I'm starting to bring all the elements to be able to interrogate all the elements at the same time in a 3D space, and I can walk around and make sense of it. In the old days, this will be presented in maybe 20 cross sections, and you will have those cross sections, and then mentally you will have to connect the dots and try to make a mental model of it, and then good luck at checking that mental model and calibrating that mental model with others. These red lines, those are some of the faults that we interpreted from looking at the core logs. And as you can see, I have a layer panel, and I can be clicking and unclicking to bring the different data sets so I can make sense of it. In the interest of time, I will move to the next video. That's at the right-hand side. You can see two of our colleagues walking at a very large model. We had to place it in our hall. Those profiles that you see, those are ERT profiles, so geophysics, and we combine them and we put them one side by side so we can make sense of it from in a 3D perspective. I will play it again. The other lines, those are borehole data, and you can see different information. I will go through it, but there's RQD, whatnot. We also have the optical televiewer information from the hole, so you can see what, maybe you can see there a little bit. Anyway, and you can see I'm on the lobby, then I go to the end on my parking lot. So you can really deploy these models anywhere you are. Another model that I really like, this is a landslide complex that I was involved in one of my projects. This is in Alberta, in Canada. You can see like very clear landslide morphology depicted here on the LiDAR data. As you can see, I can point anywhere in the map and it will give me coordinates and elevations. But more interesting, if now I go down slowly, you will be able to see the pipeline that is underneath this landslide. And not only you will see the pipeline, it's a pipeline in 3D. And there are some colors. Those colors are showing bending strains. So we use this technology a lot to highlight areas of elevated strain along this pipeline. And then we match it with the LiDAR topography, and then we can see where that landslide is moving and it's impacting that pipe. And if you look very closely down at the bottom of it, in the center of the image, and I will pause the video here if I can, there is this area where it should be straight, and you can see that there's been an uplift. You can see that the pipe has been pushed up, and that's because the toe of the landslide is just intersecting this location. It's just pushing the pipe up. This was very difficult to convey to our client by just using 2D drawings and presentations. By being able to walk around, and now you can see I'm panning around, this is far easier to interpret, far easier to communicate to different stakeholders. Other kinds of data, you can merge reality with design data, with the results of numerical modeling. The video that's playing now in light gray, that's the topography, the most recent topography DAM from a LiDAR, airborne LiDAR. The darker gray, that's the design, the ultimate elevation of the design of this dam. This is the core of the dam. And you can see how that dam, it's like vertical on its center construction, so vertical on the abutment, and then towards the center, it was inclining towards the downstream. Again, very difficult to show that in cross sections. You can see the transition here, how it transitions from vertical to the incline. Very difficult to show that in 2D drawings. It's almost, I don't need to spend time to explain it to people when you're showing it in a 3D. On the right, you can see the results from numerical modeling. Again, the limits here, it's your imagination and being able to understand what you want to show and how to show it. So you can see different results from a numerical model. On the bottom, I have a slider that I can move up and down with my finger, and I can cut through that information to make better sense of it as well. eGRAS outputs. I'm sure we have some surface water people here in the call. On the left, you can see the topography one more time, the DEM with the orthophoto on top of it. You can see closer to the river, we have higher resolution orthophoto. So that's why you see a different color. And then we have superimposed not only the flow velocities, but also the inundation area. So red, of course, it's higher velocity. The lighter colors, those are less velocity. So it's a far better way to understand this information. On the right, that's the modeling as well from, this is a dam, a water dam, and this is the spillway. Again, the water dam, and this is the spillway, and this is the modeling of how the water will be released, going under a bridge, and then continuing. I apologize, this video is not working, but again, it's the same you're seeing on the left-hand side. So you will see this model in 3D, and you will be able to interrogate that data. The fourth dimension, time. On the left, you can see how we are modeling slope inclinometer data. I could turn around, I can have more information superimposed to make sense of it. Very intuitive. You can see how that deformation is increasing with time. On the right, you can see flow lines and particle velocity. You can see those dots, how they move, and you can see that along the lines, there are some dots that are moving faster and some others are moving slower. In my experience, communicating how water moves underground and trying to explain to non-technical experts how in some areas water moves faster than in other areas, and then that will impact the transport of contaminants and lots of other things. That's a huge challenge. So these kind of models have served us in a lot of occasions, lots of projects. Let's move to case studies so you can see how we apply, how this, let's see this technology in action, for the lack of a better term. The first one, the one in the screen, this is a last chance grade project. This is a 3-mile segment of the US highway in California. As you can see, there's the left photo showing some landslides, and you can see the highway going through those landslide terrain. This road is currently open to public, but a long-term solution is needed to ensure continued safe and reliable transportation on this corridor. The landslide and road failures have been an ongoing issue for decades. And there's quite a bit of funds from the federal government here to solve this problem. This is the information that's traditionally produced. On the right, you can see those red shaded areas. Those are the landslides that have been mapped in black. That's it's the current alignment of the road, and then different colors showing alternatives. I want to focus on the left, the orange, and this will help us to understand the impact that it's creating on society. I will focus on the not only the dollar value, of course, at the top, but at the bottom left. When this road is closed, people that needs to go between two cities have to do a 6-hour detour, 6-hour path that they were not planning. For those in Europe, that will be the equivalent of driving from Barcelona in Spain to Lyon in France. So we're talking about the significant change on your plans that impacts job opportunities, that impact lots of different things. But this is the information traditionally posted on websites and presented to communities. And not only that, then we do this kind of community sessions. This is the community session. It was done in July 2018 in response of stakeholder inquiry, and because of the Caltrans is the California Transportation District. They wanted to keep the community updated. So again, this is the traditional methods, a screen with different people sitting and just listening. This is what we did. We prepared a virtual tour so participants could view site conditions from the different alternative alignments. And some of those alignments are not accessible to people because there's no road or there's no easy access. So lots of them, they will not be able to go to the field and understand it. You can see a big range of people attending that. The quote below, it was fantastic to us. Like lots of the attendees remarked that it helped them to gain a much improved understanding of the difficulties of each alternative, and it was helping them to decide which one, on their view, it was better than the other ones. Not only it was a community session, the technical experts, or the panel of experts that was supporting the American government also really appreciated the use of this technology. You can see the model on the bottom right, the video, it's showing ERT, some borehole data, whatnot. And as they said, it was an excellent aid in comprehending the site of this large landslide complex. And it was a big part of why this was a successful meeting, being the panel of expert meeting. And from the government, they say that added value in the risk assessment process itself, where it informed those experts of the terrain and the underlying spatial information. Another case study, this is the giant mine in the Northwest Territories. When the mine stopped operating and the government of Canada became the site custodian, all attention was focused on the environmental issues that were left behind. The most notable of them was the arsenic trioxide that was stored underground. And the expert says there is enough arsenic trioxide to kill the entire world a few times. So we're talking about a big problem. BCC prepared 3D holographic models that the government used to explain how they're planning to address the long-term containment of and management of that arsenic trioxide waste. On the screen, what you can see is the traditional information one more time. What we usually provide to these communities and to technical people, which are 2D drawings. So a plan view showing in green, it's showing all the tunnels underground, and in red, it's showing the areas that have contaminants. And then on the right-hand side, you have a cross-section, and you can prepare as many cross-sections as you want, showing those same tunnels in blue, and then different cavities where the arsenic trioxide is. I challenge you to make a mental model of this mine to understand the relationship between those tunnels. And not only that, then try to explain that 3D mental model to someone else and see if you guys align. And you will probably fail. Or what if worst, you will think that others are seeing what you're seeing and that you have reached common understanding. And that's very dangerous for projects. Instead, this is a video one more time, me looking through the HoloLens. You will see other people appearing. That's one of my colleagues walking through that model. In green, those same tunnels, the orange areas, those are the cavities where the arsenic trioxide could be located. And as you can see, I can just walk around that model and see the relationship between those tunnels on a way that's very easy to understand. No one needs to explain me anything. And not only that, I can see the relationship in plan view and cross-section and the relationship with the surface. More quotes. In the interest of time, I will not read them all. But to summarize, it was a key tool to communicate to stakeholders. You can see some photos of that community engagement sessions from young kids, and it was showed to elders as well. And I would like to highlight the director of this project from the federal government highlighted that they had a lot of community meetings in the past. They were presenting dead silence. People were sitting on their chairs, listening to what they had to say, standing up and leaving. He said that after they started using this technology, it was a complete shift on that behavior. Like people, as soon as they had the HoloLens in their mind, they started to point at things, they started to walk around things, and they started talking. And that's exactly what the government needs, right? Needs communities to point at issues, question about issues, to make sure, as we discussed at the very beginning of the presentation, that the project will meet society needs. This is a photo I showed at the very beginning of the panel of experts looking at this model. You can see Andy Robinson here looking down at the model. So everybody's looking at the model from the left except the woman on the right. So this is, to me, the fantastic illustration of what I was saying. Like she decided someone is pointing at a challenge, but she decided it was better to look at it from the other side, and probably she's going to call the rest. They're like, oh, come here, and I will show you. No, it looks different from here. Let's talk about that issue. They highlighted it was a very effective communication tool, both to the site workers, regulators, and to the public, and they encourage the further development and use. What else? We're getting close to the end of the presentation here. This is my iPad on a survey rod, and you can see one of our colleagues scanning a piece of the rock. You can see the model created on the bottom right. I want to highlight that this is 2 minutes of your time. You press a red button, you move left and right, up or down, you press the red button again, and that model is created. The first time I saw it, I thought it was black magic. That 3D model, not only you can share it around, but people can open it, and it's true scale, meaning that you can, and I will show some examples, you can take measurements and show it to other people. This other example was on the top left, you can see landslide morphology as shown on LiDAR data sets. I did not have high resolution LiDAR, so I could not cut a cross section. I just had a photo. So what I did, I just went to the field and I just walked that slope with my phone on my pocket. So you can see left and right, left and right, left and right. And then when I rotate that, I have a true scale profile of that slope. And you can totally see the landslide block that has gone down. And then if you put side by side at the bottom left, you will see that I put side by side that low resolution LiDAR image with my profile, and you can see that it matched pretty well those features that you can see on the image. And again, this is to scale, so it allows you to do engineering using that, of course, being mindful of the resolution. Another example, in this case, this is a me scanning with my iPhone the scar of this landslide. It's a small landslide for scale. You can see some people here on the top right using the drone. Not only I can scan it, so I have a document of how that landslide was at that specific time, but as I'm demonstrating now, I can just select 2 points and then it gives me the distance. So I know that the length was 11.3 meters and that the width was 9.5 meters. The accuracy here is my finger, right? The farther the finger, the more difficult to place those points. And now you can see that I'm looking at the height of that headscarp. And I failed miserably. I try again, and you can adjust and rotate. So it's a true scale model, 3D model that you can interact with, and you can do that in 10 years from now if I want to look back in time and see how the landslide was. More examples, you can see how we documented scour. This was in Germany. One of our engineers went on a field visit because they had big flood events, and he wanted to document the scour and erosion. On the right, you can see a pipeline. On the left, you can see scour and erosion around an abutment for a bridge. It's not perfect. You can see some gaps, but it's by far better than a 2D photo. That when you receive it, if you have not been in the field, you don't know if you're looking up, right, or left. Shout out to the education and research. On the top left, you can see UPC in Barcelona using this technology for training and to see research data. I put them here because they are really one of the pioneers in Europe at using this technology at universities. I would say them and NASCA in Rome, the University of Rome, have been the two first universities that I'm aware that are using this technology. You can see Giuseppe here wearing the previous version of the HoloLens ones. The one that he was wearing at the beginning of the call, that's the HoloLens 2. On the right, top right, you can see how we communicate engineering to little children, so they are excited about engineering and science. That was an event at the Science World. Bottom right, you can see other PhD students from Duke University and from around the world looking at different models. To close the presentation, I will show the fantastic training that we have. Like, we don't have to send people in the field anymore to show them how, if they stand on the red shaded area in front of a dozer, they will be crushed and probably die. So by walking around, as I'm doing on the screen, walking around a live scale 3D model, people can understand far better where the driver will be able to see them, where the driver will not be able to see them, and we can teach them where they need to locate themselves to monitor that construction that's going on. Now I'm walking inside that red shaded area, so on a very natural way, I can know when I will be seen and when I will not be seen. On the bottom right, you can see a photo of us doing training around drilling equipment. So where are the dangerous points around drilling equipment? And this could be any kind of training. You can train on how you prepare a foundation, how you monitor construction, et cetera, et cetera. So with this brings us to the end of the presentation. I would like to highlight three things. Robust and effective geotechnical outcomes emerge when designs are based on a thorough understanding of the geology, the environment, and the interaction of these systems over time, and it is communicated to stakeholders. The second thing, mixed reality facilitates understanding and communication of complex applied earth science problems in a more natural way. And just a note at the end, I will be in Barcelona the month of June. Of course, the UPC has HoloLens, so you could go and meet with them and they will show you that. But for any people interested, I will be in Barcelona the month of June. So, and I will bring HoloLens. So more than happy to show you this technology if you're interested. With that, Giuseppe, I will close the presentation. I will give back to you the microphone.